Hey there and welcome. Pretty much everything you see, everything you touch is built from this fascinating collection of elements. And broadly speaking, they fall into two giant families, metals and non-metals. So today we're going to dig into the secret properties that define them and see how they really do shape our entire world.
All right, let's kick things off with a little mystery. We've all been there, right? You leave a metal spoon in your coffee for just a minute, you go to grab it and yikes, it's scorching hot. But a wooden spoon, it stays perfectly cool. So what's the deal? This simple, everyday question holds the key to understanding the huge differences between these materials.
So to crack this puzzle, let's start with the most obvious stuff, the physical clues. How do these materials look? How do they feel? And what happens when we, try to bend or break them?
Think about it. For thousands and thousands of years, people like this blacksmith understood a fundamental truth just by working with their hands. They knew that some materials could be hammered and bent into new shapes, tools, armor, cooking pans, while other things would just shatter into a million pieces. And that right there, the difference between bending and just shattering, that's our first big clue. So that amazing ability to be hammered flat, it's got a name, malleability. And this is like a classic metal move. Think about the aluminum foil in your kitchen, or that super delicate silver leaf they put on fancy desserts. Both are perfect examples of malleability in action. The power to get squashed into a thin sheet without breaking. The reason this works is pretty cool. It's because the atoms in a metal can kind of slide past each other without the whole thing falling apart.
And there's a sister property to this. If you can hammer something flat, what about stretching it out? Well, for metals, the answer is a huge yes. And we call this property ductility. It's the reason we can pull metals into long, thin wires.
And ductility? Oh man, it is so crucial to our modern world. Those copper and aluminum wires that bring power to your house, that's all thanks to ductility. Same thing with the beautiful gold necklaces and silver bangles we wear. And get this, even the strings on a guitar or a sitar that create music rely on this amazing property of metals. Okay, here's another super simple test you can literally do right now. Go ahead, drop a metal coin. You hear that nice clear ring? Now drop a piece of wood. What do you get? Just a dull thud, right? That ringing quality is another classic physical property that sets metals apart.
Okay, so we've covered how they bend, how they stretch, even how they sound. But that's really only half the picture. To really solve that hot spoon mystery, we need to look at how these things handle energy, specifically the flow of heat.
And boom, here's the answer. That metal spoon gets so hot because it is an amazing conductor. It just sucks up the heat from the coffee and lets it flow super easily right up the handle to your fingers. See, metals have this unique structure, almost like a sea of electrons that are free to just zip around. And those little electrons are perfect for carrying energy, like heat, really, really fast. Wood, on the other hand, is a poor conductor. It basically traps the heat right where it's touching the coffee.
And this whole conductor thing, it's not just about heat. The exact same principle applies to electricity. You can see it right here. In a simple circuit, you hook up an iron nail or a copper wire, and boom, the bulb lights up because the electricity can flow. But swap that out for a piece of coal or wood, both non-metals, and nothing. The circuit's broken. The bulb stays dark.
So here's the bottom line, the big showdown. On one side, you have metals, awesome conductors. They let heat and electricity just flow right through. On the other side, you have non-metals, the poor conductors, or what we call insulators. And this one single difference is why an electrician's tools have plastic handles and why they wear rubber gloves for safety. It's literally a lifesaver.
Okay, we've looked at the physical side of things, but to really get what makes a metal and a non-metal, we have to look at their chemical fingerprint, like how they react with everyday stuff like air and water. All right, check this out. This is an incredible puzzle from history. In Delhi, there's this iron pillar that's been standing for more than 1,600 years, and it has barely any rust on it. How's that even possible? It's this amazing feat of ancient metalworking. But to figure out how they did it, we first need to understand, what's the basic recipe for rust anyway?
So it turns out the recipe for rust is actually super specific. Step 1, try an iron nail with just dry air. Result, no rust, nothing. Okay, step 2, try an iron nail in water, but with no air, still nothing. But step 3, combine that iron nail with both air and water, and there it is, rust. You absolutely need both ingredients or the recipe fails.
So this whole process of a metal breaking down like that, it has a scientific name, corrosion. Rusting is probably the most famous type of corrosion, but it's really just what happens to iron. Other metals corrode too, like when copper gets that green patina or silver turns black.
And this brings us to a really deep, fundamental chemical difference between these two families. When a metal reacts with oxygen, it creates something called a basic oxide. But when a nonmetal, like say sulfur, reacts with oxygen, it forms an acidic oxide. You can prove this with a simple litmus test. They give you the complete opposite result. It's like their chemical signature is a total mirror image.
All right, so they bend differently, they conduct energy differently, they even react with the air differently. So, what? Why does any of this actually matter in the real world? Well, let's zoom out for a second and see the incredible world these properties have allowed us to build.
Think about it. Because metals are strong, but also bendable, we can build massive bridges and tiny, precise tools. Because they're ductile and great conductors, they literally power our world through all that electrical wiring. Their crazy unique properties even let us do things like explore space and harness atomic energy. Yeah, from giant skyscrapers to the simple cooking pan in your kitchen, metals are pretty much the backbone of our entire civilization.
Okay, so what about the non-metals? They might not be flashy, building our skyscrapers, but you could argue their job is even more important, even more fundamental. I mean, the oxygen you're breathing right now, that's a non-metal. The nitrogen that's absolutely vital for the fertilizers that grow our food, also a non-metal. The chlorine that makes our water safe to drink, the iodine that we use as an antiseptic, all non-metals. They are, literally, the elements of life itself.
So you see, in the end, it's not really metals versus non-metals, it's a partnership. We absolutely need both. From the iron atoms carrying oxygen in your own blood, to the silicon that powers the chip in your phone, we are built from and surrounded by all these different elements. Their unique properties have built the world we live in, and all of this leaves us with one last really exciting question. What are we going to build with them tomorrow?